You are welcome to Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Computer Arithmetic Part 2. Today, we are going to further look at computer arithmetic. But before we start, please follow me in this lecture series by subscribing to my YouTube channel at https://youtube.com/@Ndinechi Like, share, and drop your comments in the comment section. We have also done some introductory lectures on computers in module 006, which you can see in that link. You can also listen to our other lectures on computers, which is module 014 from part 1 to 7. You can also listen to part 1 of this so that it will be easier for you to follow. So today we are going to continue by looking at the hexadecimal numbers. When we talk of hexadecimal numbers, we are talking of base 16 numbers. And base 16 numbers employ 4 bits to represent decimal numbers from 0 to 15. The least significant bit in front of the hexadecimal point is assumed to be weighted 16 raised to power 0, which is equal to 1. We have said that if you have your bits, the one to your right is the least significant figure or least significant bit. So the next is 16 raised to power 1. The next is 16 raised to power 2, and so on. So if you look at that example, you will see that to your right, which is 16 raised to power 0, is weighted 1 in decimal. The next 16 raised to power 1 is rated 16 in decimal. And the next one, 16 raised to power 2, is weighted 16 times 16, which is 256 in decimal. So if we take an example, 368 raised to base 16 will be equal to 3, which is the most significant bit, times 16 raised to power 2, plus the next one, which is 6, times 16 raised to power 1, and the next, which is 8, times 16 raised to power 0. If you do that, you see that 3 times 256 will give you 768 in decimal. 6 times 16 will give you 96, and 8 times 1 will give you 8. So if you total it, you will now see that 368 to base 16 is equal to 872 in base 10, which is decimal number. So if we are counting in base 16, which is hexadecimal, it means that after 10, we will continue to count up to 15. And after 15, we go back to 0. This will be a bit cumbersome to human beings. Therefore, figures in the range of 10 to 15 are assigned the first 6 letters of the alphabet. Thus, 10 is assigned A to represent it, 11 is assigned B to represent it, 12 is assigned C to represent it, 13 is assigned D to represent it, 14 is assigned E to represent it, and 15 is assigned F to represent it. So now, computers make use of binaries, you have said before, but we know that 4 bits or 4 binary bits we represent any hex number, because the maximum we have in hex is 15. So if you convert 15 to its binary equivalent, it will give you 1111. And we say that 111 represents F, or we use F to represent 15. So to convert from binary to hexadecimal becomes very easy. So we say to do that, you have to form the hex number equivalent of any binary number you want to convert. Group the bits, the binary bits, in fours, starting with the least significant bit. Then replace each group with its equivalent hex digit. For example, if we are to convert this string of binary numbers to its hex equivalent, we say we start from the least significant bit, which is the rightmost bit. We group them in fours. Starting from the right, 4, 4, 4. So if we group this bit, you see that the first 4 bits will be 0011. The next 4 bits will be 1111. The next 4 bits will be 1000. And the next 4 bits will be 1011. Now, 0011 is equivalent to decimal 3. 1111 is equivalent to decimal 15, but we won't write 15, we use F to represent it. 1000 is equivalent to decimal 8, and 1011 is equivalent to 11, which we use B to represent. So we just put down that the hex equivalent of that string of zeros and ones will be B84, B8F3 in base 16. If you want to convert or do the reverse process, that is converting from hex to binary equivalent, you just put each of these hex number its binary equivalent. It gives you what you want. Now, why do we bother ourselves to do this? Because in computers, we hear words like, or jargons like neighbors, bytes, and word length. So say that a neighbor is a sequence of 4 bits. That is, any 4 bits you put together in computer terminology is known as a neighbor. Of course, we hear byte every day. So a group of 8 bits is known as byte. Example, 0101, 0001, which is 8 bits, is known as a byte. The other thing we hear is the word length. The number of bits used to convey data in a computer or microprocessor is known as its word length. Binary patterns representing numbers and instructions are stored in the computer memory. Each binary pattern or word, consisting typically of 1 or 2 bytes, has its own location in the memory, and each location is given an address quoted as hex number. In our previous lectures, we've tried to, talk about memories. So each computer has a memory map, and this memory contain a byte, which is a group of 8 bits. Normally, these bytes are, called the lower byte or the upper one, but we'll get to that later. So let's do an illustration. Let us determine for a 1 byte computer which stores data in memory locations from address locations B000 in the 16 to BFFF in the 16. And we are required to determine the decimal equivalent for the first and the last address. Here, the first address is B000 in the 16, and the last address is BFFF in the 16. The second question there is to determine the amount of binary data in bits and bytes that can be stored in the memory of such a computer. So let's, quickly look at it and see how it can be done. The address location, which is B000 in the 16, we were told is the beginning of the address location. So we find its decimal equivalent. And we say that you just put in from the least significant bit, which is the one on the right, we give weightings of 16 raised to power 0. Because the multiplying factor is 0, give 0. Then the next one is 16 raised to power 1. Because the multiplying factor is 0, it gives 0. Likewise, the third one. But the fourth one, which is 16 raised to power 3, has a weighting of B, which is 11. So we say 16 raised to power 3 times 11 will give us 45,056. So we will say that 45056 in base 10 or decimal is the beginning of the address location. Likewise, we do the same thing for the final address location. When we do that, you see that the first one, which is F, that is the least significant bit of the 4 digits, is F, which is 15. It becomes 15 times 16 raised to power 0. Of course, we know that anything raised to power 0 is 1. So it becomes 15. Then the other one, 16 raised to power 1, like that, we progress to the left. So at the end, we sum it. When we sum it, it will give us 49151 in base 10. We say, therefore, the number of individual locations between B000 base 16 and BFFF in base 16 is 49151, that is the last address, minus the beginning one, which is 45056. If we subtract that, it will give you 4,095. That is 4,095 different locations. But then we have to add one to represent the starting address, which is the B000 base 16. If you add that one, it gives you a total of 4,096 address locations. So the second question, which is asking us to find the total amount of data that can be stored, say that each location stores 8 bits, and we have 4,096 locations. So the total amount of data that can be stored will be 4,096 times 8, which is 32,608 bits. So, or we just say that it is 4,096 bytes, since 8 bits equals 1 byte. So you see that we've been able to find the number of bits, which is 32,768 bits, or its equivalent in bytes, which is that number divided by 8, since 8 bits is equal to 1 byte. So at this point, we have to note that the size of computer memory is often measured in units of 2 raised to power 10, which is 1,024 locations. This unit is designated 1K. So when you see a computer, or when you are looking at something and it is described as having 1 kilobyte, it means you are looking at 2 times 10, which is the 1,000 or 1 kilo. So note also that the 24 difference from the convention, you normally know that 1000, which is 1,000, is called 1K. But for the binary or computer memory, when we say 1K, there is always a difference on top of 24. So thus the storage space between B000 and BFFF16 is 4,096 bytes. Now, if we move it to K, we divide it by 1,024. If we do that, it gives us 4 kilobytes. And since the microprocessor has a word length of 1 byte, it then means that the amount of information stored is 4 kilobytes, or 4K times 8 bits, which is 32 kilobits. We'll quickly look at, start moving away from just looking at bits to see what the computer will see, instead of just continuously looking at zeros and ones. And that leads us to what is known as binary coded decimal, otherwise known as BCD codes. Because of the everyday use of decimal numbers, it is very useful in many microprocessor and computer applications to code each decimal digit by an individual group of bits, which is known as the neighbor, which is equal to 4 bits. Such codes are referred to as binary coded decimal, normally abbreviated BCD codes. So this BCD is a special form of binary code in which each decimal digit is expressed as a 4-bit pattern. A number of different BCD codes are in use. Perhaps the most popular of them all is known as the 8421 BCD. In this 8421 BCD, the most significant bit of the 4-bit group is weighted 8. The next is 4. The next is 2. And the least significant bit is 1. This allows us to define uniquely any decimal digit by 4 bits. Note the distinction from pure binary coding. In this BCD code, 6 out of the 16 possible 4-bit binary groups, 1010, 1011, 1100, 1101, 1110, and 1111 are not used. So please try and figure out why these combinations are not used in the 8421 BCD codes. Drop your answer or what you think in the comment section. In the next one, which is the 2421 BCD code, the most significant bit has a weighting of 2, the next a weighting of 4, the next a weighting of 2 again, and the least a weighting of 1. We also know that this BCD code enables the computer to be able to assign the sign of the numbers. For instance, the number you are looking at could be a minus sign, it could be a plus sign. So as we go on, we'll be able to see how the computer manipulates these zeros and ones, and now be able to append the sign of the number to it. The BCD code helps it to do that. We also have another code which is called the XS3 code. And in this XS3, it is usually adding decimal equivalent 3, which is 0011, to each of the 8421 BCD code. So when you do that, it gives you a table like this. On the left, you see the decimal numbers from 0 to 9. You see the 8421 BCD code, which is equivalent to the binary equivalent of the decimal code. Now, the next is the 2421 code. So if you look at that, you see that the code changes. Then on the right, you see the XS3 code, which is adding 0011 to each of the 8421 BCD code. That gives you that. So if we take the 2421 BCD code as an example and look at decimal equivalent 9, you see that decimal equivalent 9 in the 2421 BCD code is 1111. Now, the first one, which is the least significant bit, carries a weighting of 1. The next one carries a weighting of 2. The next one carries a weighting of 4. The next one carries a weighting of 2. Because the multipliers are 1111, it becomes 2 plus 4 plus 2 plus 1, which is equal to 9. So likewise, any of those 2421 BCD code, the equivalent decimal number can be found. So we are going to stop here for today. We are hoping that we will improve, and in our part 3, we are going to make it possible for you to be raising your hand, putting up your questions in the chat section, so that as I go through the lectures, I will be able to see your questions in the chat box and respond to that. Thank you for listening. And